Number 2 attempt, guys. Apparently I didn't turn on the microphone, so I guess that's just part of life. We're talking about classification this week. As you can see in the little video, there's a person sorting paper, plastic, cardboard, things like this. Classification methods are, and I'm sorry I'm so yellow. I have no idea what's going on. I've checked all my video camera. I've checked every setting I can figure out. I guess I just look yellow this week. But classification methods are a really unique thing in the business world. They're very popular, and yet we sometimes don't always talk about them. We don't always discuss them because they're almost built into some of the programs that we use. So they're unique. But before I get started on that, let's go over a couple things just to make sure we're all on the same page. So here's where we're at, week 9. We're not quite at the end of October yet. So we're at 10:23 to 10:29. Classification methods. There is no discussion this week. Again, why is there no discussion? Why is there no homework? At the end of each month, I want to make sure I allow you ample time to provide me a phenomenally perfect project. I want to make sure that everything you do is perfect for these big projects. Please check the spelling. Please have the other team members contribute. If you have questions, please submit to me a draft or something. I've already had probably about a third of the teams, 2 or 3 teams, submit me samples. I'm like, yeah, no, change this. Just giving real general help. Here's a better data set, things like that. Please submit to me by, let's say, the 27th. The 27th, maybe morning of the 28th. So if you get it to me late the 27th or early in the morning before noon on the 28th, I'll look at your data research project or your data analytics project. After those days, I'm not going to look at it. Now, continuing down that road of just good business practice, what is the 31st? It's Halloween. And who knows what can happen in Halloween in Vegas. Okay, your roommate might get in a DUI, heaven forbid. You might go out trick-or-treating and you might somehow lose power. If it was me, since I, the teacher, the professor, allow unlimited uploads, I would upload it the 30th. Even if it's not 100%, just upload something the 30th, upload something the 29th, doesn't matter. Upload something before it's due. Then you can work on it the 31st and tweak it if you need, and then re-upload it. But what I would not do is wait till 11 o'clock on the 31st, upload one copy and just forget it. So again, I allow unlimited submissions. I don't care how many times you look at, or how many times you upload submissions. I don't look at any of those unless for some reason you really want me to. I don't look at past submissions. Just upload it 30th, just as a fail-safe. Upload it again on 31st if you need to. My advice, you can do whatever you want. Please don't be late. And if you're late, I take a lot off, like half. Okay. Additionally, I only need one submission from your team. Okay. If I go people and I go groups. So group number 4 today is Claire, Kim, and Charles. If I get 3 submissions, I don't need that. I need one submission from one of these people. So just one submission from one person will do. Group number 2. Okay, one person just needs to upload it. I don't need 3 uploads. Okay. So let's just recap real quick. We are here. Classification methods. This lecture is mostly didactic. I'll go over that here in a bit. Classification methods are even more classification methods than there are regression methods. So there's a lot of different things to go over. I'm not expecting you to know any of these in great detail. I just want to give you a cursory review of these different methods, which I'll do here in a minute or two. I have 2 workbooks. One classification, decision tree. I found a couple demos online and just basically coded it out by hand. I took a couple ideas from a couple people and just made it a million times better. There's also an SVM model. I just literally Googled Colab SVM and grabbed the first notebook just to explain some basic ideas. So this week, no homework, but there is a Python demo. Next week, when the actual assignment's due, when we go to clustering will be done in Tableau. Tableau does clustering very well. It's very easy to do. So we'll do clustering in Tableau. We might do T-sign or PCA in Python. I'm still not sure. I keep going back and forth. Okay? So this week's going to be a little lighter week, especially compared to regression. And we'll go in there from there. Your data analytics projects. Let's just cover the expectations. I wish I could share it with you. I'm waiting for approval to share it with you. But I found this Optim map thing. And basically it outlines, hey, here's a business problem. Here's the data we're going to use. Here's how we fix the data we're going to use. Here's what we found. And they made it in a web page, but you could make it in Word just as easy. And that's kind of what I'm hoping to gather from you. Define the problem. Find and understand the problem. Okay? Data cleaning. If you remove outliers, that's fine. Just maybe a sentence or two as why. Further exploration. Hey, and that means that, hey, in next year I plan to interrogate this data more. Or I did a real quick descriptive statistics, and I noticed this wasn't right. So that is further exploration. So, hey, here's a problem. Here's some of the data we found. Now here's how we're going to analyze it. We analyzed it, and this is what we found. Here's data visualization. And you can also probably just Google white paper examples and find some stuff here. Okay, the final report should focus on the business problem, the goal of how the data will solve the business problem, and a few visualizations. Remember, visualizations, keep them straightforward and make sure they very clearly convey the key findings. They can be made in Excel, Tableau, Python, which is misspelled, I'll fix that, or anything else. Where's it at? Or Python. They can be made in R. If you're comfortable with R, that's fine. Please use a non-technical, clear, concise language to ensure understandability for upper management. Ensure that insights and recommendations are backed by data and robust analysis. Please have only one team member upload the final report in a Word or PDF format. Thank you. See, do the 31st. If you have questions, again, please email me. You guys should have already been working on this. Everyone's doing fine on that. So, okay. Next kind of announcement. Somebody asked me about a general statistical program. I use JASP. JASP is, I think it was from a European grant. So they have like the NIH here in America, the CDC, and all that. They have the same thing in Europe. But I think the JASP is, I don't know, I probably can figure it out here. Yeah, from Amsterdam, it's, I think somebody basically, they just got a grant and made this really cool program. So what JASP is good at? JASP is good at doing a lot of basic statistics. Not basics, I mean ANOVA, t-test, linear regression, generalized model. So it does a lot of the tests that you want to know maybe up front. It makes really pretty graphs. So I use JASP when I'm just when I get new data and I want to kind of poke around and see if that data is valid. I'm not, let's see if we go features. I'm not going to cover JASP. You can download it if you want and play with it. But here, free descriptive, t-test, ANOVA, mixed models, regression. They can do factoring. I mean, a ton of stuff. Cochrane test for meta-analysis, like systematic reviews. You can do some machine learning, power calculations. It does some time series stuff, some summary statistics. It makes pretty looking graphs. Let's see, as an example. So like I said, it's a really nice little. It's fast. You upload a CSV, or it connects to databases. Yeah, it reads all these formats. So it's a nice little program. And so if you're looking for a program just to say, hey, do I have something of significance here? Jasper will at least get you in the ballpark. Hey, I want to do summary statistics to make sure I'm not missing too much data. You can just dump it into JAS. So somebody just asked about that. Figure I'd share it with the class. So we have the weekly plan done. We have this. If you want to review it, Friday the 27th or by noon Saturday, I'll look at your project. Shall we dive in? Let's not waste any more time because classifications you could spend a whole class on. Actually, I'm going to turn off the video because I hate being yellow. So we could spend a whole class, a whole semester, just looking at classification, supervised classification methods. There's a ton of different ones. And at the end of the day, classification methods basically break down to two things. If it's continuous variable, continuous output, it's a linear regression. It's a regressor model. If it's not a continuous output, it's a classification. Now you might think, why do I want classification instead of actual and exact value? Because a lot of times all we need to know is a yes or no. When I go walk down to get my mail and I'm looking at my mail, I just need to know, hey, is this junk mail or is this not junk mail? I need to know pass, fail, is this junk mail? I don't need to look at an envelope and say, if I tell my wife, hey, there's a 78% chance this is junk mail, go to the next letter. There's a 92% chance this is a bill, go to the next one. There's a 47% chance that this is junk mail. She'd look at me like I'm crazy. So supervised learning and classification say, this is junk mail, this is important, this is junk mail, this is important. Very, very simple process, and that for a lot of business applications is very important. So classification helps make informed decisions by categorizing data into specific buckets, which then can be analyzed for patterns and trends. It also enables business to understand key, I don't have the word there, key customer behaviors by categorizing them into various categories. Is this customer likely to spend money on Black Friday, yes or no? Is this customer likely to apply for a credit card, yes or no? And then if they say yes, then I can go on and derive additional intelligence from them. Once I classify them into a bucket, I can do more with them. But I basically generated a beautiful, I don't want to use that word, a focused data set. Risk management. Businesses can identify and categorize potential risks, enabling them to implement mitigation strategies proactively. Targeted marketing. By classifying customers into different segments, businesses can create more targeted marketing to cater to the specific needs and preferences of each segment. So let's dive in here a little bit more. So, the churn prediction, which again, I've never been a big fan of teaching that, but if we think about it, if we know what customers are likely to not be customers anymore, we can start to interrogate as to why those customers aren't going to be customers anymore. Okay? And we don't want to do this for the whole group. Maybe we want to just grab customers that are likely to leave, then grab the, hey, these are customers that are likely in the next 6 months not to be customers anymore, to cancel our account. These are customers that are likely in the next 2 years not to be customers. So once we have that basic core information, then we can dive deeper into that. Credit scoring. Do I want to give this customer a line of credit, yes or no? Spam detection. Is this spam, yes or no? If it's spam, it goes on junk mail, we never see it. Fraud detection. Now, fraud detection is a unique case, and this is one reason that classification methods are really unique. Just my thing's not lined up. Sorry about that, guys. In a lot of what we do in machine learning or in statistics or in business intelligence, we want balance. I'm not talking about some Zen balance. I'm just talking about equal distribution between two groups. At least semi-equal distribution. So, if we're looking at the difference between spam and non-spam, My training set, in theory, should be balanced. I should have 500 spam emails and 500 non-spam emails. This way, I can make an accurate prediction. Well, one of the nice things about classification is we can do these, we can do very extreme, very unbalanced type of training. So I might have 1,000,000 authenticated non-fraud transactions and one fraud detection, or one fraudulent transaction. That type of unbalanced transaction, or that type of unbalanced data set would be hard to do in any other model. So the big three, let's see if it goes on to this. Oh, no, this one. So when we looked at linear regression, which is the one on the right with the y equals whatever plus x plus the coefficient, we're trying to find the best fit line through that. We're looking for continuous output. So we know that, I don't know if I can pause it, I can't. So when I'm at, I don't know, 150, I should be able to predict out here what my value is. Okay, so this is linear regression. We're trying to find a best fit line, the least error. When best fit was to say least error, least residual. Now, with classification, we're approaching it differently. We want to separate the two data sets into yes and no, into a different bucket. Now let's think about this for a second here. And there's a reason I put these two kind of GIFs on this page. So if I own Walmart, or I own some type of business, or I own Amazon, I want to know the first graph. Are people likely to go shopping on Black Friday? Yes or no? So that is my first classification system. With the people that are yes, likely to go shopping on Black Friday, then I can get a linear regression model from those people saying, hey, if I offer them a 10% discount, how much more are they going to spend? If I offer them a 20% discount, how much more are they going to spend? Or I can look at any other factors related to that. But I know that I'm looking at only my customers that are likely to go shopping on Black Friday. So the key takeaway from that is that classification has discrete outputs. Where linear regression, or just regression in general, multiple regression, has continuous output. So regression, I'm trying to predict a continuous value. Classification, I'm trying to predict a discrete value. Sometimes it's multiple labels. Red, blue, green, cat, fish, dog. We'll go on that in a second. But I'm trying to predict a very discrete value. Regression, I'm trying to predict a continuous value. That's what makes these so valuable in business. Types of classifications in machine learning. Well, there's binary, which we've talked about. Is it spam, not spam? Is it fraud, not fraud? Multi-class classification. So that first video of the recycling, where we had paper, cardboard, aluminum, that would be a multi-class classification. And if I'm holding an aluminum can, I go to the paper bucket or paper recycle bin. Is it paper? Yes or no? No. Go to the next one. Is it compostable? No. Is it metal? Aluminum is metal? Yes, so it goes on the metal recycling. Multi-class classification, the example I use on here is cat, fish, and dog. If I was to say, hey, St. Bernard, that goes into the dog bucket. If I said German Shepherd, that goes into the dog bucket. If I said Siamese, that goes in the cat bucket. If I said Koi, it goes in the fish bucket. They're discrete buckets. Okay, they're very discrete buckets. Now, multi-label classification is more of a newer term, but that's when one label can have, or one label can have multiple labels attached to it. If I'm looking at a picture and there's 2 or 3 people in the picture, let's say there's 3 people in the picture, there's 3 people in the picture, One person could be happy, one person could be sad, and one person could be angry. So I apply multiple labels to a single data point. But they're not, it's 80% happy. No, I have happy attached to that data point. Image segmentation used to be a lot more clustering. We'll go into clustering next week. Like I said before, we're going to do clustering in Tableau. But now it's more of a classification problem. It's slowly shifted toward the classification problem. I think I have 10 more types of classification, but these are, these are ones that you need to always kind of think about. These are the big players. These are the ones in my mind that are valuable as a classification. So imbalanced classification, identifying the minority class among an imbalanced data set where one class heavily outnumbers the other. And in many systems, in many algorithms, or in many machine learning methods, this is very, very hard to do. But in classification, you can do it. Fraud detection, where the number of non-fraudulent transactions is significantly higher than the fraudulent ones. Anomaly detection, detecting outliers that are significantly different than normal data. This is often used in cybersecurity. The example I give is detecting fraudulent credit card transactions in a data set where most transactions are legitimate. How do we know that that outlier is a natural outlier or it's a fraudulent outlier? Cost-sensitive classification. Here's a unique one. Well, we can apply, a false positive, true negative, and we can say, hey, a bad loan might cost us significantly more than denying a good loan. Okay, so minimizing the costly errors by assigning different miscalculation costs. This is used in medicine too sometimes, where we don't want to give a chemolytic, a toxic drug, to a person that does not have cancer. Sometimes it's more important maybe not to detect slow-growing cancers than to over-detect them and give a poisonous material to somebody to make a healthy person sick. Hierarchical classification, ordinal classification. Ordinal classification, predicting the rating of a product from 1 to 5 stars, but the difference between 1 and 2 stars might not be the same as the difference between 4 and 5 stars. So there's non-uniformity built into the data. Oops, I went the wrong way. Sorry about that, folks. Let's see what else we got. I know I got some more. Ensemble classification. So random forest. Random forest is a collection of decision trees, which builds multiple decision trees. I'm going to go over a demo. Today's demo is going to be a decision tree. One class classification, time series, and predicting the stock movement. So I know what you're thinking. Hey, Richard, time series and stock prediction, that's a linear regression. That's a machine learning. I want to know what is the price of the stock tomorrow. Yeah, a lot of people do that. But what if I had a model that just said the stock's going to go up? Well, its choice is, hey, it's going to go up or down tomorrow. That's all I care about. Is the price of the stock going to go up or down tomorrow? I know if it goes up tomorrow, I will hold on to it. I know that if it's going to go down tomorrow, I'll sell today. I don't care how much it goes up. I don't care how much it goes down. I just want to know tomorrow, is Apple stock going to go up or down? If it goes up, I'll continue to hold on to shares. If it goes down, I'll sell my shares. Okay. Stream classification. Here's a neat example of classification that we use, that a lot of people use in business. So we have a massive amount of data coming in all the time. We look at Twitter or X. We have maybe millions of tweets a second. I have no idea how many, but let's say we have 1 million tweets a second. Well, I can't realistically and economically run all 1 million tweets a second through some type of machine learning model. But what I can do is run them through a quick classification model. So that job of that classification model is to say, hey, is this a valid tweet or is this a hate-based speech tweet? Is this a normal tweet or is this a not normal tweet. Once I flag it as a not normal tweet, then I can go and interrogate with different methods why it is not a normal tweet. Okay, so again, with like the Black Friday example, a couple slides back, where I separated out, hey, here's the people that are most likely going to spend money on Black Friday, these people that aren't going to spend money. Once I have differentiated the two, I have a better inherent data set. So let's keep going here. So classification is basically there's two types. There's linear and nonlinear. Okay, so a linear problem, as you can see here, it can be easily separated. You can basically draw a straight line through it. We've already talked about this. Credit approval, yes, no. Medical diagnosis, yes, no. Spam detection, yes, no. And remember, these can be either individual points or they can be a collection of points. Okay. Now, what about nonlinear classification? This is where classification gets neat and fun. So I can't draw a single straight line through that two-dimensional graph. But I have to figure out a way to separate it out. So nonlinear classification methods, while a little bit more complex, can do that. So nonlinear classification refers to algorithms that do not have a linear decision boundary. The decision boundary can take on various shapes depending on the complexity of the model and the data. Nonlinear classifiers are particularly useful when data is not linearly separable, when there's not a straight line or a hyperplane in more than two dimensions that can be separated as well. When I review the SVM model, we're going to talk about kernel trick. A kernel trick is basically to move this data to a three-dimensional model, and once it's in a three-dimensional model, I might be able to draw a straight line through it. But now let's talk about overfitting and fitting. I'm hoping that you've heard and understand the basics of an overfit model, an underfit model, and a good or generalized model. But often people ask, why is overfitting bad? And it's a very valid question. It's a very, very valid question. Why would you not want this super accurate, super highly accurate model that I created? What are the withdrawals? What are the downfalls? And let's think about it this way. If me and you were to get an elevator, and we're on 10 stories, we have, 30 seconds till we get to the ground floor. And I ask you, why is overfitting bad? What would your answer be? And I want you to think about that because it's a very important concept. And there's a bunch of different reasons why overfitting is bad. But one of the most obvious ones is that we can't use that model. That model is not transferable. That model is not generalizable. Those are terms you'll generally hear. So if we have an overfit model, we can't train it or we can't use it to predict new data. Okay? So if I have Black Friday sales and I have some type of model for 2020 and it's overfit, it will not predict data for 2021 or 2019 very well. So if we think about this, when I told you a couple weeks ago, I went out to lunch with the CS professors, and what they do for their midterm and their final is they give test questions. So that they'll give you like a fake midterm with similar questions on it. You have to take that kind of fake midterm home, review it, look at it, and use it as a study guide. We've all had classes like this. Now, if that fake midterm, or that, I guess, that practice midterm, if it had nothing to do with the real midterm, if it had nothing to do, if I'm in a biology class and I get a fake midterm, and the first question is on it, hey, I want to do a derivative of this, or hey, Rene Descartes is famous for saying what? Aristotle's major contributions to philosophy or what? And you're sitting in a biology class, you're like, oh my God, I have no idea. That's an underfit diagram. That's an underfit model. It has nothing to do with the model you're trying to train it on. An overfit diagram is the exact opposite. An overfit diagram is when the sample midterm questions are too similar to the real midterm, and you can't really use that data for anything else. And I know that's kind of hard to comprehend, but it's a very, very important thing, because a lot of times when we get to these nonlinear models, overfitting does become a problem. And what happens is we overtrain our model, we get these overfit models, and then we can't generalize them to new data. We can't ingest new data. We can't grow them. We can't do more with them. So when we design a model, we want it to be a good fit, not underfit, not overfit. This is a great article. Now, I do know that you have to have a membership, so I'm going to go over the article here real quick. Okay, so here's this article. Let me make it a little bit bigger. Let's magic, make it bigger. Okay. Yeah, I think that's my paid account. Okay, so logistic regression. We talked about regression a little bit last week, but basically this is yes, no. We can do this a couple different ways. We can put some type of function at the end of it that just basically forces it to do yes or no. I'm not worried about that right now for this class. Decision trees, we're going to have a demo of decision trees. And I hope that, this decision tree, I try to make it as simple as possible. That when you go look at the code and you look at the graph it makes, it comes out very, very clear. You can like, oh my God, I can make decisions with this. This is actually something that I can separate my data into. Or this is something that is very valid. Okay, and when we do the demo, I'll show you. Random forests become a little bit more complex, just inherently because you have multiple decision trees built upon one another. Now, support vector machines, they're very, very popular SVM. And the general idea of an SVM is, if I have that data, you can kind of see it back here. If I was to try to just generally linearly separate that, there's a couple different ways I could do that. I could take, all the average of all these, dots, draw a line, take an average of all these dots, draw a line, and try to figure out the difference. And there's a lot of problems with that, because we get multiple lines, we get intersections, things like this. So what makes SVM special? SVM is special because basically it looks at the border. It looks at the very edge. So SVM might say, hey, what are the 2, 3, 4 closest dots to your enemy, to this other set right here? And what are these? What are the closest 2 or 3 dots here, data points, to this set over here? Okay, now that I have the closest 2 or 3 here, closest 2 or 3 here, how can I maximize the margin between these two? It becomes very useful for a lot of things, face detection, a bunch of different things. Next nearest neighbor, KNN, is a general abbreviation for this. KNN is a way we look at how can we cluster or group. I don't want to use the word cluster. How can we group things together based on the proximity to what's around them? Okay. And again, scikit-learn, I believe, has built-in databases to do all this stuff automatically. So again, to do this, you literally just copy and paste this in here. There's some sample data. Let me pull that up here real quick. So if you want to dive into any of these, I mean, this is so easy, so nice to do. I should have thought about this before I spent all that time doing that decision tree. Because I don't see decision tree's not on here, maybe. Oh, it is. It's right there. My decision tree is better. It's colorful. Okay, so classification method. So this is all scikit-learn. So if I wanted to learn how to do bi-clustering, where is classification? There we go. Classification. Plot classification. What do we have here? Quadratic LDA. Okay, so just copy and paste it. Boom. It automatically imports a data set. Or it might give you a data set. I'm not really sure on this one. And you see, I mean, it gives you everything you need. And it explains this is exactly the output you'll get. So you can mess with some of the variables. You can really kind of launch the binder. You can actually play with it in real life time. And it takes, what, 1/3 of a second to run? Let's go back to what else I have for classification. We'll say numbers, handwriting. So why do we use classification with handwriting instead of some other type of classifier or some other method? Well, because we want to know that, hey, it might, it might say, hey, this is 80% of 1 or 20% of 7. So what we want to do is we want to force its hand. We want to say, hey, this is definitely an 8. This is definitely an 8 or 9. So we want to force it. We want to force its hand to make a decision as far as what it is. And it won't always be right. You can see here, it's out the 6 and it said it was a 1. But the thing is, though, once we force its hand, we can do it much quicker. So again, scikit-learn and classifiers. So decision tree, this is what the demo is gonna cover like this. Random forest is a collection of decision trees like that. It's a common type of ensemble learning, which aggregates results. Compared to decision tree, it has better generalization, but less interpretable because it has more layers. It becomes harder. SVM. SVM finds the best way to classify data based on the position and relative to the border between the positive and negative class. The border is known as the hyperplane. Okay. KNN. KNN is an algorithm, and there's some great graphs on how KNN works. Like if you just do, let me find one real quick for you. There's this one, there's another one, but you can basically see how it looks at 5 of its neighbors, puts kind of Euclidean distance in between the two. I mean, you see here how it goes over to blue because more of its neighbors are basically blue. We can go into KNN. KNN is very popular because it's very fast most of the time. Yeah, you can use it for movie recommendations. How can you use it for movie recommendations? Well, if I like these 3 movies, you might like these 3 movies. I'm not going to go into Bayesian yet. So that pretty much sums it up. I'm going to do the demo. Again, one demo is decision tree. Like I said, I found a couple sample pieces of code, but I rewrote most of it. I think it was Python 2. It was pretty bad code, pretty messed up code. And then I have an SVM demo. So let me do those demos. And then have a good week. Email me if you have any questions about your project. Thank you.